Hello viewers, welcome to another exciting video. In this video, we will be looking at the July 2021 Science Paper 1, which is basically the GCE paper for 2021. And in this particular case, we are looking at question C3. Now, question C3 is coming from a topic that is very well known to those writing the exam, and this is atomic physics. It is the topic that is commonly called radioactivity. So, question C3 reads, the atomic number of americium-241 is 95. Americium-241 decays by losing an alpha particle. The atomic number of americium-241 is 95. Americium-241 decays by losing an alpha particle. A1. Explain why smoke detectors containing americium are not harmful to people. Explain why smoke detectors containing americium-241 are not harmful. All right. Basically, here we are talking about human safety. So when we talk about human safety, we need to look at what things are protecting a human being from this radiation, knowing that radioactive radiation may cause cancer. Okay. Now, understanding that americium is emitting an alpha particle there. So what do we know about alpha particles? What we know about alpha particles is that alpha particles can be stopped by one, pepper. However, in the design of these smoke detectors, they do not put pepper, because if they put pepper on the smoke detector, it will be unable to perform its function, because all the radiation, it depends on the radiation. Okay? It depends on the radiation. So they leave it just open. Now, if they leave it open, then we are exposed, right? No, we are not. Because alpha particles can be stopped by a few centimeters of air. So them just traveling a small distance in air, covering just a few centimeters, they are easily absorbed. They are easily blocked by air molecules. So one, okay, they are not harmful to us because they are stopped, or they are blocked by a few centimeters of air. Then even if we were exposed to the little amount that so manages to get to us, our skin is more than sufficient to stop them. So why aren't they? Why isn't americium harmful to us? One, because because alpha particles can be stopped by a few centimeters of air, and also by our skin. So we are going to say because alpha particles so our skin is more than enough to stop them. So if it is blocked before it gets to the cells, then well and good, we are safe. All right, we go to A2. A2 is saying copy and complete the equation showing this decay by giving values for x and y. Copy and complete the equation showing this decay by giving values for x and y. All right, this is an alpha decay. This is an alpha decay. So first and foremost, you need to know the general decay equation for alpha. Okay, so in this particular case, we will have our parent nuclei, the parent nuclei with atomic number Z and mass number A. All right, so when the parent emits an alpha particle, what remains, the nuclei that remains, is called the daughter. And in certain books, it is written by the letter Y, okay? The letter Y. And what happens to the atomic number? The atomic number reduces by 2. And the mass number also reduces by 4. So you just say the mass number of the parent minus 4, or the atomic number of the parent minus 2. Then this is accompanied by an alpha particle, which is a helium nuclei, which is 2, 4. That is where the 2 and the 4 are going. Then plus the energy that is always produced. So this is the general decay equation. However, we've been given a specific decay equation. So we are going to use the correct symbols that we've been given. Instead of using X and Y, okay, we are going to use the correct symbols. So allow me to wrap the general equation. Or maybe I try to find space somewhere just underneath the americium there. So what we're going to have is, we have americium, Am, and underneath it's 95. On top there it's 241. Okay, 241. This will decay by emitting an alpha particle. So the alpha particle is there. So they started with the alpha particle. There is no harm. Then we have a 2 there and we have a 4 there. Then this is accompanied by the daughter. The daughter is given NP. Now what we're going to do is, we will refer to the general equation. So we are going to say the atomic number of the parent, which is 95, minus 2. That will be the atomic number of the daughter. So 95 minus 2 is 93. All right? 93. Then, when it comes to the mass number, we are going to say the mass number of the parent minus 4, which is 241 minus 4, which is 237. So we'll have 237. So the values of X and Y, the value of Y, the value of X is 237, the value of Y is 93. Okay, then this will be accompanied by what? We've been told there is energy there, so plus energy. So the values of X and Y are there, 93 and 237. So that ends us those 2 marks. Now we proceed to B. Okay, we proceed to B. Okay, question B says figure C 3.1 shows how the activity of a sample of americium-241 changes over a long period of time. Figure C 3.1 shows how the activity of a sample of americium changes over a long period of time. All right, so let's look at the beginning. So we've got there the time. Time is given in years. The activity is given in counts per minute. All right. At the beginning, the activity was 64 counts per minute. After 500 years, it reduced to 30 counts per minute. After 1,000 years, it reduced to 14 counts per minute. After 1,500 years, it reduced to 6 counts per minute. After 2,000 years, it had reduced to 2 counts per minute. Okay, now having that information, we go to B1. B1 is saying use these numbers to draw a graph of activity against time for americium. Okay, use these numbers to draw a graph of activity against time for americium. All right, so first things first, we go to our graph paper. So this is our graph paper, okay? The axes have already been drawn. So you're supposed to draw these axes yourself. And I say that the best place to draw your x-axis is just on the first line from the bottom. The first line from the bottom, which is this line. And for the y, it is the first line from this side. So once you do that, it means that your graph, you can draw your graph on the biggest possible space you have. Now, remember, your graph, in your mind, you should always know that your graph should occupy 3/4 of the graph paper. However, sometimes they are lenient. So always ensure that it occupies more than half of the graph paper. Always ensure that your graph is as big as possible, in short. It should not be small. They give you an A4 paper so that you can cover, okay, more than half of the A4 paper. Your graph is on an A4 paper. So the first things we say, okay, to have a good graph is one, the title. Where do we get the title? When they tell you draw a graph of, so they're saying activity against time. That is the name of our graph, activity against time. So we come, and on the top there, I'm going to write activity against time. Now, take note, I did not use capital letters for the whole entire title. Therefore, I'm obliged to underline the title. If it was in capital, you can leave it without underlining it. But if it is, you've used small letters, then you need to underline. All right, next. The next thing is you are supposed to label the axis. You are supposed to label the axis. Now, the title itself will tell you which physical quantity is going on the y-axis and which one is going on the x. So the first quantity on the title goes on the y. So activity goes on the y. Time goes on the x. It's x against it's y against x. Y against x. So activity y, time x. Now these should be with the units. So we come back to our table. So they've given us that time is in years. So, and activity is in counts per minute. So I come, okay, I come down there. So I'll label the y-axis as activity all right, so activity, there we have activity in brackets counts per minute. Then we go to the x-axis. We go to the x-axis. On the x-axis we have time, so we are going to write time open bracket in what? In years. Okay, once you do that, out of the 4 marks, be rest assured that you have at least 1 mark because you have the title, you've written the title, okay? You've labeled the axis correctly, okay? Which is activity with the units for activity, time with the units for time. Now, we go to one of the most critical parts of our graph plotting. So we need to come back here to see how our scale is going to be. So here on the time axis, we are starting with 0. Okay, 0 is the smallest number there. Okay, on the time axis we've got 0. Okay, and according to our graph paper, okay, we are supposed to cover as much as possible, and according to our standard ECZ graph paper, it has about 10 boxes on the X side, and we have about 12 on the Y. So we need to occupy as many boxes as possible. In most cases, 8 boxes. If you occupy 8 boxes, you are safe. Okay, now looking at away from the X, I turn my attention to the Y. The smallest value of Y is a 2. Okay, so I can easily say that 2 is very close to 0. So I can choose by starting at 0, 0. So if I choose to start at 0, 0, it means I need to write my 0 there. So that is 0, 0. Now, what I do is, for the time axis, I need to use about 8 boxes. So let's see if when I say, because 2000 minus 0 is will obviously give us something like 2000. It is 2000. So 2000 divided by 8, because I need 8 of them. So I'll say 2000 divided by 8 this gives me something like 250, if I'm not mistaken. 250. Okay, yeah, 250, because 2000 divided by 4 is 500. Half of 500 is 250, so it gives me about 250. So it means that every box increases on an interval of 250 years. So let's try and see how it looks like. So from 0, I come to this box will be 250. The next box, 250 plus 250 is 500. The next is 750. Okay. The next will be 1000. The next 1250. Then I have 1500. 1750. Then I have 2000. I think it has occupied as many boxes as possible, and the intervals between each the size between each interval is the same: 250, 250, 250. Okay, so I have there. So how many boxes have I used? 1, 2, 3, 4, 5, 6, 7, 8 boxes. So I have about 8. 1, 2, 3, 4, 5, 6, 7, 8. I've used 8. So I'm safe. So it is more than half. It is more than half of from the beginning of the X to the end. So I'm safe. Now take note. Don't worry so much about the 3/4. Always make sure that the difference between the smallest value and the biggest is more than half of your graph paper. That really helps. So we turn our attention to the y-axis. Let me just rub those. Okay. Okay. Let me rub those. Okay. Let's turn our attention to the y. So y on the y-axis. On the y-axis, I have activity. The biggest number for activity is 64, and the smallest is 2. Okay, so in this particular case, I said 2 is very close to 0. So since the graph is starting at 0, 0, I can say 64. 64 divided 64 minus 0 is 64. 64 divided by 8, it's 8. Okay, it's 8. However, I can decide to go with 8. Okay, I can decide to go with 8. So it means that what I'm going to have is from 0 here, I'm going to have 8. Okay, then 8 plus 8, I'll have 16. 16 plus 8, I'll have 24. 24 plus 8, 24 is 32. 32 plus 8, 32 plus 8, it's 40. 40 plus 8, 40 plus 8, it's 50. 40 plus 8, it's 48. 40 plus 8, sorry, it's 48. 48 plus 8, it's 50. 48 plus 8 is 56. 56, not 55, 56. Okay, is that correct? 8, yeah, 56. 56 plus 8 is 64. All right, it's 64, meaning that now if you do this, okay, you've slightly you've slightly complicated your life, but it's fine. Okay, it's fine. Okay, it's fine. What we just need to know is that what is the different what is the size of this Casmo box. However, our graph will be is as big as it as possible. Then we can start the plotting. So allow me just to extract my table here, so that we move with it, so that we don't keep on coming here. All right, we go back to our graph paper. So the first point is 0 years when the count rate is 64. So 0 years, so 0 is here, and the count rate at this particular point is 64. So this one is relatively easy. So we are going to have our first point there. That is where our point is. Or maybe allow me to just change the color so that these points are different. So allow me to use blue. Okay, so our first point is there. Okay, our first point is there. We go to the second point, which is 500, 30, 500, 30, 500, 30. So this is where 500 is. Okay, that is where 500. Now we locate 30. Now, what we know is that this very small box is 0.8. Okay, it's 0.8. So what we are going to do is we're going to say 32 minus 0.8. It will be 31.2. 31.2 minus 0.8 again, that will give us 30 point, okay, allow me to look for a calculator. Allow me, okay. So we have 32 minus 0.8, which is 31.2. 31.2, that is the first box. Then again minus 0.8. This gives me 30.4. 30.4 is okay. So I've subtracted two 0.8s, which means I've moved two boxes down. So I've moved two boxes down from 32. So our 500 is here, and from 32, I'll move the first box, brings me to 31.2. The second box brings me to 30.4. So the reason why we put a cross is to say the point is somewhere in this vicinity. So we are safe, okay? We are safe. If you are using points, you circle your point, meaning that your point is within the circle. The point is within the circle. Then we go to 1000, and it is going with 14. 1000, which is here, and it is going with 14. So 14, since our 1000 is here, 14, we are going to say 16 minus 0.8. Okay, so we go back to our calculator. So we now have 16 minus, because we are moving down, minus 0.8, which is 15.2. Okay, again minus 0.8, which is 14.4, which is 14. So again, we're just going to move twice from 16. So 1000 is here, 16 is here, so 1, 2, so our point will be here, and we put a cross there. So that is where 14 is likely to be. Okay, then we go to 1500, 6. 1500, so 1500 is here, and 6 is slightly below 8. 6 is slightly below 8, so we'll go to 8. We'll now have 8. 8 minus 0.8, it's 7.2, minus 0.8, which is 6.4. So again, we move twice, 6.4. So from 8, we have 1, and we have 2. So it's here. So, there. Then we go to the last point, which is 2000, 2. So 2000 is at that point. So for 2, we can move from 0. We start adding until. So we know that when we add, this will be 0.8, this will be 1.6, and this will be 2.4. So it will be somewhere in that vicinity. So it will be somewhere here. So this is where our point will be. That is where our 2 is going to be. So now, at this particular point, what we're going to do is, I'm going to close that. I'm going to close that. Okay, since we've already plotted the points, now we need to connect these points. This is a curve. Do not join them with straight lines. You need to use free hand. So what I'm going to do is I'll start by connecting these last 1, 2, 3, 4 points. So it's a curve. Okay, it's a curve. It's a curve. So I go back to black. So it's a curve. So I need to be careful. It should be smooth. So I start from that, from the last point. So I'll start from there. I start coming. Okay. Then I will now connect that to the last point. Allow me to zoom out so that, so no, it should be a smooth curve, so there should be continuity up to that point. Yes, so that is my graph. If you look at it, it's smooth and it's a curve. So that is my graph. So I've plotted the graph. I've plotted the graph, all the 4 marks there. 1 mark for correctly labeled axis, 2 for the scale, the third correctly plotted points, lastly a smooth curve. Those are the 4 marks. Those are the things you should always look out when plotting a graph. Now we go back to the question. We are done with the question B1. We go to question B2. Use your graph to find the half-life of americium 241. Use your graph to find the half-life of americium 241. So here, what we do is, you just say, okay, at the beginning I had 64. What is half of 64? Half of 64, which is 64 divided by 2, is 32. So you need to look for 32. Where is 32? 32 is exactly here. Then what you are going to do is, with this 32, you are going to draw a line there following the 32 mark. Okay, where this touches the graph, you start coming down following it, just like that. You need to show this because they've told you to use your graph. So you're going to use a rule. I cannot use a rule because of the screen. So this is what I want. Okay, this is what I want. All right, now in this particular case, it has landed just a box short of 500. However, it has landed just a box short of 500. All right, so now I have to determine the value at that particular point. So in our x-axis, one of these boxes represents 25. So we're just going to say 500 minus 25, which is 475, meaning our half-life is 475 years. 475 years. So you're now going to write half-life is equal to 475 years. So you've determined your half-life. So that is your half-life. All right, let's go to question number C now. Okay, question number C. Californium-241 is also radioactive and decays by losing an alpha particle. It has a half-life of 4 minutes. Suggest why it would be unsuitable for use in smoke detectors. Now, here the reason why it is unsuitable is because it has got a short half-life, meaning that it will take less than a day for californium to almost go to completion. Okay, therefore the smoke detector will stop working in the first day. Before it even leaves the factory, the smoke detector is not effective. So because of that, californium is not suitable to be used in smoke detectors because it has got a short half-life, a very small half-life. Thank you very much for watching this video. If you're new to the channel, please don't forget to give it a thumbs up. If you're new, don't forget to subscribe and hit the notification bell. Thank you very much. Have a blessed day.